Hey guys, it's Miss Johnson, and I'm here to bring you our first notes for section 7.1. We're getting into chapter 7, and we're going to talk about sampling distributions. So the first thing to distinguish is the difference between, a couple of definitions here, a parameter and a statistic. So a statistic is a number that describes some characteristic of a sample. For example, the mean or the standard deviation. You can have a mean of a sample, and that's a statistic, okay? The parameter is a number that describes a characteristic of a population. So you can also have a population mean, which is like a true mean, but we all know that finding the true population mean or the true population standard deviation is a really hard thing to do depending on what your population is. So statistics go with samples, and what that helps because the letters go together. Statistics go with samples, and parameters go with population. So keep your samples and your statistics together and your parameters and your population together. One other thing to kind of make note of is sometimes you will hear the phrase point estimator. A sample statistic is also sometimes known as a point estimator. Again, that's just depending on what you're looking at. If they're talking about a whole population, but then they break it into a small group and they say this is the point estimator for the small group, they're really getting at the fact that that's the sample statistic. All right, so let's just talk about an example here. It says identify the population, the parameter, the sample, and the statistics in each of the following groups. So for A, we're looking at a Gallup poll, which is a company that does a lot of surveys for a lot of different people and organizations in our country. A Gallup poll asked 515 randomly selected U.S. adults if they believe in ghosts. Of the respondents, 160 said yes. So for part A, the Gallup poll, your population is all U.S. adults. The parameter, or sorry, I should go in order here. Yeah, population, then parameter. So the parameter is the U.S. adults who believe in ghosts. And we don't know that number. It's not going to be possible for us to find that number, but that's what we're looking at. U.S. adults who believe in ghosts. Then the sample is the 515 U.S. adults, and the statistic is the 160 U.S. adults that believe in ghosts from the sample. So you've got the side that's the population, and you've got the side that's the sample. So sometimes you're looking at it big picture with the whole group, but again, that's really hard to see sometimes to make a calculation off of. And then you're also looking at a lot smaller piece, the sample, which is typically what we will be analyzing in this class. Okay, so I'm gonna do some erasing here, and then we're gonna look at part B. So in part B, it says, during the winter months, the temperatures outside the Starnes' cabin in Colorado can stay well below freezing for weeks at a time. To prevent the pipes from freezing, Mrs. Starnes sets the thermostat at 50 degrees. She wants to know how low the temperature actually gets in the cabin. A digital thermometer records the indoor temperature at 20 randomly chosen intervals during a given day. The minimum reading is 38 degrees Fahrenheit. So for B, you've got the population as all times during the day, which is an impossible population for us to calculate because time is a continuous variable. So you have seconds and, infinitely number of times between each second to the next. So it's impossible for us to gather data on every single piece of time in the day to get the whole population. So the parameter would be the true minimum temp. Minimum temp at all times of the day. Now, because that's an impossible thing for us to calculate, she takes a sample. So the 20 times that she randomly chooses are her sample. And then the statistic is the sample minimum temperature. Or in other words, 38 degrees Fahrenheit. Okay, so again, you can look at things in terms of big picture with a population and a parameter, but population and parameter is not always easy for us to calculate or find. So then we take it on a smaller scale and take a sample. And then we can do the sample and the statistic and use that data to do our analysis. All right, so AP exam tip, we already kind of talked about this. Keep your letters together. Remember the S's and P's. So statistics come from samples, parameters come from populations. And here's your AP exam tip. It says many students lose credit on the AP exam when defining parameters because their description refers to the sample instead of the population. So just be really careful. If you're talking about a parameter, you have to use the term population. If you're talking about a statistic, then you can use the word sample. It says when you're defining a parameter, we suggest including the word all or the true mean, like we said, true minimum temperature, things like that will help you get to at the point that you're talking about the actual population and not just a sample. Okay, so let's just talk about the idea of what a sampling distribution is. So I'm going to go back to sampling variability. Sampling variability refers to the fact that different random samples of the same size from the same population produce different values for the statistic. If I look at Farmington High School, for example, if I pull 100 students and get the average height amongst them, I could pull a different 100 students the next day or later that day and have a different average height. So is it still an appropriate sample? Yes, but sampling variability allows for the fact that I'm not going to get the same mean just because I pulled 100 people in both samples. I'm still pulling 100 unique individuals, and that's going to adjust my my sampling mean in a slight way. So that's what's happening here. The sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the same population. So when you are looking at a sampling distribution, you're looking at every possible combination of however big your sample size is. If I was pulling 100 people from Farmington High School, I'd have tons and tons and tons of different varieties of pulling 100 people. There's tons of different ways that you could get 100 people in your sample from the students of Farmington High School. The sampling distribution would be a collection of all of those possibilities, okay? Sampling distributions are not always possible to collect. If we wanted to do that, it would take us a really, really long time to make every single possible unique group of 100 from our 2,500 students or however many we have. So sampling distributions are unique in the way, or are hard to get in that way, because you have to look at every single possible group. Okay, so you're going to see a sampling distribution. You're going to start looking at dot plots again, and it's going to look like the simulation graphs that we looked at back in chapter 5 when we talked about pulling things for improbability. We had simulation after simulation after simulation. Well, a sampling distribution kind of looks like that. You're repulling a new group of 100 people. You're repulling a new group of 100 people, repulling a new group of 100 people. Or in this case, it's a sample mean of 5 years. Or a sample mean year out of choosing a group of 5. Your sample size is 5. So how many different ways can they pull the 5 groups, and then you get the mean year? I'm not even sure what this example is on, but you get what's happening. You've got an n equaling 5, and they found the mean. And these are all of the possible groups of 5. All of these little x's here are all of the possible groups of 5 that exist in their sample. Okay, so that's what makes it a sampling distribution. It kind of looks like a simulation graph. The concepts are pretty similar. In other words, it's really just repeating the process over and over and over again. Just like in probability, we would repeat the trials over and over and over again. Now with samples, we're going to repeat the sampling process over and over and over again. Pull a new sample of 5, pull another sample of 5, pull another sample of 5, and so on and so forth. All right, so John and Carol have 4 grown sons. Their heights in inches are 71 inches, 75, 72, and 68. List all 6 possible samples of size 2. So if you're pulling a group of 2, okay, all 6 possible samples of size 2, you could have 71 and 75, 71 and 72, 71 and 68. You could also have 75 and 72, 75 and 68, and then 72 and 68. Now, I'm not going to go through the hassle of listing 75 and 71 because that's the same group. It doesn't matter the order I pull them in. I just need to have 2 unique individuals in each thing. So this is 1, 2, 3, 4, 5, 6 different samples. There's 6 different samples that you could pull from each of those, from those 4 people of size 2, I should say. Then it says calculate the mean of each sample and display the sampling distribution of the sample mean using a dot plot. So really I want a mean of each of these things. Okay, I slid my second column over there a little bit over to the right so I had some space. So in part B, I want to create in purple, and I'm just going to write them up next to the group above. So in part B, I want to create the sampling distribution of the mean of this data. So grab your calculator and just go through and find the mean of each group. Now, finding the mean of something that's only 2 units in size is really easy. So I'm just going to take 71 plus 75 and divide it by 2, and I get 73. So that's going to be my mean there. 71 plus 72 divided by 2 is going to be 71 and a half. 71 plus 68 divided by 2 is going to be 69 and a half. 75 plus 72 divided by 2 is going to be 73 and a half. And again, all I'm doing is finding the mean here. 75 and 68 divided by 2 is going to be 71 and a half. And then the 72 and 68, that's going to be 70. Duh. Sometimes I start typing things into my calculator even though I already know the answer, but I do it anyways, just to check myself. Basic math, you know. Anyway, okay, so now it says display the sampling distribution using a dot plot. So if I'm going to display the sampling distribution, I'm going to have the mean height in inches of n equals 2. Sorry, that was supposed to be an of, not an on. N equaling 2. So my means go from 69 and a half up to 73 and a half. So I need I'm going to start at 69, 70, 71, 72, 73, 74. Label those. 73, 74. And then fill in your means. So I've got one mean right here. I've got one mean, I'm going to start at the top, 73, 71 and a half. I already did 69 and a half, 73 and a half, another 71 and a half, and a 70. Now, you could just use a dot if you wanted. I did the X bars to signify that it was a mean. It doesn't really matter. You could have just done a dot, which you're going to see these things as dots more often, especially when your sampling distribution is really large. If you had a lot of points to put on this graph, then you're probably not going to do the X bar because that just takes up more space. So you could do the X bar or you could do the dots. Then in part C, it says calculate the range of each sample and display the sampling distribution of the range using a dot plot. So if I come back up here, I'm going to do this in blue. So my range here is 4. I have a range here of 1. I have a range here of 3. I have a range here of 3. A range here of 7. And a range here of 4. So my ranges are in blue. Here's my dot plot. Sorry, I'm getting really small down here. So the range of heights in inches of size 2, groups of size 2. And I need to label my graph from 1 up to 7. So 1, 2, 3, 4, 5, 6, 7. And I'll use black for my little points here. So I have, and I forgot to label those, sorry. 2, 3, 4, 5, 6, 7. So I have a dot at 1. I have a dot at 4. I have a dot at 3. I have another dot at 3. I have a dot at 7, and I have another dot at 4. That's my range of the data for the entire sampling distribution. Okay, so we're going to take a look at our next example here. This one says, to determine how much homework time students will get in class, Mrs. Lynn has a student select an SRS of 20 chips from a large bag. The number of red chips in the SRS determines the number of minutes in class students will get to work on homework. Mrs. Lynn claims that there are 200 chips in the bag and 100 of them are red. When Jenna selects a random sample of 20 chips from the bag without looking, she got 7 red chips. Does this provide convincing evidence that less than half of the chips in the bag are red? So the first part A here, says, what is the evidence that less than half of the chips in the bag are red? So in Jenna's sample, the probability of getting a red was 7 out of 20, which is only 0.35, which is less than 0.5. Okay, so right there, her first sample, her one sample, does show that it was less. Part B says, provide 2 explanations for the evidence described in Part A. So it is possible, there's 2 ways of looking at this. It is possible that Mrs. Lynn is telling the truth and that Jenna got a p-value that was less than 0.5 because of sampling variability. Okay, so there's that first possibility, but the other possibility is the fact that Mrs. Lynn is either lying or has the wrong number of the number of red chips in the bag. So that's your other scenario. So she could be wrong or lying about that number, and it could actually be less than 100. All right, so we're going to look at Part C. It says we use technology to simulate choosing 500 simple random samples of size n equals 20 from a population of 200 chips where 100 are red and 100 are blue. The dot plot shows the p-hat equaling the sampling proportion of red chips for each of the 500 samples. There is 1 dot on the graph at 0.8. Explain what this value represents. So at 0.8, there was 1 SRS of 20 chips in which there were 16 red ones, giving p-hat equaling 0.8. In Part D, it says, would it be surprising to get a sample proportion of 7 out of 20 or 0.35 or smaller in an SRS of 20 when p is equal to 0.5? So again, here's your simulation. This is your sampling distribution. So what we're looking at is 0.35 or smaller. So 0.35 or smaller is like all of these. So the point here is when you look at that group, you're looking at all of those responses there. You've got quite a few that are at the 0.35 level, and you've also got some that are even lower. You know, you've got a bunch at the 0.3, a bunch at the 0.25, and one down even at 0.15. So in this case, no, it's not that surprising. And that's where we get into what is your significance, okay? So we look at this simulation, we look at the probability, the sampling distribution, we look at the value that is our point of interest. For us, it was 0.35, and we determine, is it unique enough to say that, yeah, this is surprising, or is it not unique enough where we would say, no, it's not really surprising for us. There's a bunch there, so it's not that surprising that she would get us one sample like that. Okay, one last example of this question. E, based on your previous answers, is there convincing evidence that less than half of the chips in the large bag are red? So because it is not surprising to get a p-hat value of 0.35 or less, then there is not convincing evidence that the bag is wrong, because it wasn't surprising. It wasn't surprising for us to get 0.35. If it's not surprising for us to get 0.35, then we can't say that there's convincing evidence that she has the wrong number of red chips in the bag. So here's how I would write this out. Because it is not surprising to get a p-hat value of less than or equal to 0.35, there is not convincing evidence that there are less than 100 red chips in the bag. Okay, so again, this sampling distribution idea is to take many samples from the same population of the same size, collect the value of the statistics from all the samples, and display them in a distribution, typically a dot plot. So then the dot plot shows the approximate sampling distribution of p-hat, the sampling proportion of red chips. So they're just showing you that, like, here's your population. That's your population. Here's a couple of the random samples. This one we pulled had 8 out of 20. This one we pulled had 11 out of 20. And then you go ahead and graph them on the approximate sampling distribution. Now I want to talk about this word approximate for a second. They call it the approximate sampling distribution because they didn't pull every single possible group of 20 chips out of the bag. That would be impossible to do unless you numbered all the chips. Okay, so they call it the approximate sampling distribution because it's not possible to get the actual sampling distribution. So there's just a little tidbit there for you. The population distribution gives the values of the variable for all individuals in the population. The distribution of sample data shows the values of the variable for the individuals in the sample, and the sampling distribution of the same proportion displays the values of p-hat from all possible samples of the same size. Okay, so population, showing the population parameter, sampling, the distribution of sample data is right there, and then putting them in the sampling distribution dot plot is there. Okay, one more AP exam tip. So it says, never just say, terminology matters is what they say. Never just say the distribution. Always say the distribution of whatever. You have to name your sampling statistics. So be careful to distinguish the distribution of a population or the distribution of your sample data or a sampling distribution of a statistic like the mean. You need to describe or elaborate on what the distribution is saying, because there's a lot of distributions that we will create in this class. So you have to be really particular about how you describe it. Okay. If we just say the sample distribution, we could be referring to sample data or sampling distribution of a statistic. And it says you could lose credit on a free response question if you're misusing statistical terms. All right, we reached the end of the first video. So we're kind of jumping back here in this chapter 7. We're going to go back to that discussion of simulation. We're also going to go back to the discussion of probability. We're also going to combine it with some normal distribution stuff here soon. So yeah, hang in there. We're putting some connections together. Thanks for tuning in, and I will catch you next time.